There's one more vector space associated with matrices that we need to discuss. So again, let's let A be an m by n matrix. The null space of A, which we denote null of A, is the set of all vectors x in Rn such that Ax equals 0. Okay? In other words, it's the set of all vectors that solve the homogeneous equation where A is the coefficient matrix. All right? Now, the null space is defined a little differently than how we define column space and row space. The column space was the span of the column vectors of a matrix. The row space was the span of the row vectors of a matrix. We are not defining matrix or the null space of matrix A in terms of a span, though, which means it's not immediately clear that the null space of A is a vector space. We know a span of vectors is a vector space. We've seen that before. So column space, row space, that's definitely a subspace of Rn. But the null space of A, we don't know if that's a subspace. So we need to prove that that is a subspace. Now, fortunately, it's a fairly straightforward proof. So let's let A be an m by n matrix. Then the null space of A is a subspace of Rn. Okay? So remember, a subspace is a vector space, but it's just it's a vector space that is a subset of Rn. Okay? Now we already know the null space is a subset of Rn. We're taking all vectors x in Rn that satisfy some condition. So everything in the null space of A is in Rn. To test if a set is a vector subspace, we need to check that it's closed under addition and it's closed under scalar multiplication. All right? So let's first check addition. So let's let two vectors, let's say x and y, be in the null space of matrix A. Now remember, to be closed under addition, that means the sum would also have to be in the null space of A. X plus y would also have to be in the null space of A. All right? But before we jump into what x plus y is, note that because x and y are in the null space of A, that means, by definition, to be in the null space, that means if we take A and multiply it by vector x, we get the 0 vector. And if we take A and multiply it by vector y, we get the 0 vector. Right? That's what it means to be in the null space. Then what we want to do is we want to show that if we take x plus y, it's also in the null space, which means A times the sum would also be equal to 0. But A times x plus A times, if I distribute the A, I get A times x plus A times y, which is Ax is equal to 0, Ay is equal to 0, so I get 0 plus 0, which is 0. Thus, the sum of two vectors in the null space is also in the null space of A, meaning the null space of A is closed under vector addition. Okay? We still need to show that the null space of A is closed under scalar multiplication. If it's also closed under scalar multiplication, then the null space of A is a subspace of Rn. So I've already got some arbitrary element of the null space of A. I need a scalar. So next, choose an arbitrary scalar. k in the set of real numbers, so an arbitrary real number scalar. Then I need to show that if I scalar multiply an element from the null space, it's still in the null space. In other words, I need to show that if I take x and multiply it by k, that this is still equal to 0. Okay? But scalar multiple, remember, with a scalar multiplication and matrix vector multiplication, I could move the scalar wherever I want. So I could, for example, move it over here. And a times x, because x is in the null space of matrix A, is just 0. It's just the 0 vector. And then if I scalar multiply the 0 vector, I still get the 0 vector. Okay? Which means that kx is also in the null space of A, because to be in the null space of A just means if you take A and multiply something in its null space, you get 0. And so since I'm taking A, and when I multiply it by kx, I get 0, that means kx is in the null space. And if it's in the null space of A, that means I didn't assume anything special about the scalar. The scalar could have been any scalar. I didn't assume anything special about vector x. X could have been any vector in the null space of A, which means the null space of A is closed under scalar multiplication. And if the null space of A is closed under addition, and because it's also closed under scalar multiplication, that means it's a subspace of Rn. Those are the two conditions I need to check.